Hello everyone, welcome back to Project Pro YouTube channel. This is me Simran Anand, and in this video I'm going to be explaining you a really interesting topic of artificial intelligence and data science, which is object detection. I'm going to be explaining you what is object detection and how different it is in context of image classification. What are the various project ideas you can get started with by implementing object detection, and will be explaining you what are the different models in deep learning which exist for project detection and what are the differences between them. So let's get started. So basically, object detection is a computer vision algorithm or a task which helps us in not only classifying images into different categories, but also in localizing the objects present in a different image. So basically, take for example, you have a video or an image. So video is basically a combination of different frames, image frames, or an image which is having many pixels, because image, as you know, is a combination of pixels. So how exactly are we able to detect or classify the different objects present in an image? So that can be done if we can basically build a deep learning or a machine learning model that is be able to detect the objects present in an image by drawing a bounding box, and also giving us the some kind of a measure or a metric to help us identify where exactly the object is located in the image. So that is where, when we're talking about images or videos, there is where convolutional neural networks will come into picture, because as we know, convolutional neural networks, they operate on image data sets. So where basically, if you have an image of different objects, so how exactly the CNNs are able to actually give us the exact location of the object present, and how exactly what are the different values which are being assigned to the pixels. So that is exactly done by a property of CNNs, which is called as translation invariant, because CNNs, what they have is basically the share weights. So they are able to basically capture the different patterns present in an image. And because of that, the CNNs are able to, because of the transposition property, they are also able to detect where exactly in an image an object is present. So before getting into the technical terms about what is object detection and how exactly it is different from image classification, let me give you some real life examples where you think an object detection must be very applicable. Say that in a basically in a traffic system where you have where you want to know that which vehicles are passing by. So you must have heard about the vehicle plate detection as one concept or one project. So basically, that is where we are drawing a bounding box over here. As you can see, an image is there. We are going to take an image consisting of various objects. So when we talk about the plate detection, so when we have cars and the different vehicles present, we are going to draw bounding boxes. Basically, we are nothing but the green boxes you can see on my screen. They are nothing but the rectangular boxes. So they are used for basically capturing or detecting the objects present. Now we have to understand what exactly we are detecting. So that target object is set by us. So for example, say we are talking about in a context of this particular traffic system, where on the road we have the different vehicles present. So in order to classify the objects, or along with that also assign them the metric, the coordinates, basically where exactly they are present. So along with object detection, object localization should also be done. That is where we are going to make use of object detection. So in such cases, have you ever wondered that where exactly object detection can also come into picture? So when you say you have CCTV in the real news, where you have CCTV cameras, or say whenever you want to basically detect objects using surveillance systems, that is where object detection is coming into picture. Also, it has several other applications, like in the context of whenever you want to monitor in an area where social distancing norms have to be followed. So mask detection, face mask detection is one other project which you can get started with for object detection. So basically, when you have an image or a video consisting of different image frames, how exactly are you able to identify or capture the objects present in that particular image is nothing but object detection concept. I hope I have given an introduction to you what exactly is object detection. Now this can come handy in different use cases. So in this video, we are going to understand what they are, what are the different project ideas ranging from the beginner level to the advanced level. This is the Project Pro website. You can also go through them to get started with the different object detection projects. And then we'll be looking into what are the different CNN architectures and the different object detection models in general, and how different they are and which one is required in what context and which solving which kind of use cases. So when I say a flower recognition model, basically you can take any data set, right? Data can be taken from Kaggle or can be taken from any other image sources. You can also build a own customized data set of yours, taking images by manually downloading them from various websites and so on. So the data collection can be done by you accordingly. On that, you can build this flower recognition model. Say you have a set of data set having flowers in different backgrounds. How exactly are we able to capture which kind of flower it is, the class of the flower? So that is where we can make use of different object detection techniques. So over here, it's mentioning a very prominent object detection technique you might have heard of, that is called YOLO, which is you only look once. We'll be looking into what exactly is YOLO. Before that, I'll just explain you what are the different projects you can get started with. So this is one example for you. Another is a face mask detection model, which I was talking about. So basically, in order to understand whether an image present, and say if you have an image of people wearing a mask and other ones without a mask. So how exactly is our model able to identify the image, basically wherever you give it for training? So the model should be able to capture the patterns, the general patterns, and then whenever you're passing a test image of a person wearing a mask, the model should accurately detect that the mask is present in the particular image, and with some kind of a score or a measure, which can be an accuracy score in our case. We can set the metric accordingly, but then some kind of an objectness score should be there, or a coherence score should be there, so that the object present in that image can be correctly detected. That is where face mask detection can also be applied, because over here basically whenever you're talking in terms of social distancing norms, it's very important for us to monitor or build systems in such a way to ensure that the CCTV cameras or any such real time, when you're tracking people in the real time, the people present in a particular area are following the social distancing norms by wearing masks and so on. So in such cases, to identify accurately whether to distinguish basically the images into two categories, where there's one without a mask and one with a mask, that is where you can use object detection concepts as well. So not only that, but there is real-time object detection, as you can talk about. So when I say real-time object detection, it need not be static images. You can have dynamic images of moving objects as well. So when I was showing you in the start of the video and a context of the traffic system where you are having different vehicles which are actually moving, the image which I shown you, I was actually static. That was only containing an image of different basically captured photograph of basically the captured photograph of all the vehicles which are static, because they already are moving in real, but then the image is static image because it's the vehicles are not moving. But then if you have an image like a GIF or some other image which is containing dynamically moving objects in present, how do you think that object detection can actually be applied in those areas as well? Definitely you can make use of object detection not only for static images but for dynamic images as well. And not only that, but you can also do it in terms of whenever you have video data set. So video, as you know, is a combination of frames, image frames, and they all are having different objects. So whenever the objects are actually moving or in motion, you can make use of real-time object detection system. And over there again, YOLO is one such model, and YOLO has different variants, like starting from version 1, YOLO V1, V2, V3, and so on till V8, because YOLO V8 also is a recently developed one. So as you know, there you can build a real-time object detection model based by making use of this concept of object detection. You can definitely explore the different data sets, and you can basically the different pre-trained models. So YOLO is a pre-trained model. We'll be looking into detail what and how different it is from the other object detection models as well. But YOLO we are using very widely it is used because of its high accuracy and the less training time it takes as compared to the other models like fast RCNN or RCNN models, which I'll be explaining you in the later part of the video. So basically in the real time as well, you can make use of the basically predict the objects present, because they work on image frames, as I told, which come in with the pre-trained model you loaded. So not only that, but you can also build a animal detection system where in order to this is a simple object detection model, whereas it can not only be moving objects or vehicles. When I say object, they can also be real living objects as well, living human beings or animals, plants, and so on. So you can also make use of this animal detection system to classify the images, and of course the convolutional neural network is ones which are used to build the model. So this is some of the beginner level projects you can explore. Then you have the shape detection model. Basically, you have as the name is self-explanatory. You have a set of images consisting of different shapes, and how exactly are you able to assign classes or classify the different shapes which are present in a data set. That can be done again by making use of these, basically finding the contours of the image. Now, what exactly is this contours? You will come into that context when we are talking about edges. So basically, contour is something like when I say the features of an image. So as you know, convolutional neural networks, they have to, firstly, you're passing some input image, set of input images to your convolutional neural network. A convolutional neural network consists of different layers in it, and starting from the 2D layers, and then the max pool layers, and finally the dense layers. So max pool layers, before that you have all the non-dense layers basically. Then you come to the dense layers, then the max pool layers, and finally the fully connected neural network or fully connected layers of your CNN. So what exactly are these layers, the roles of these different layers? So when I say max pooling layer, that comes towards the end of your neural network, just before your fully connected layer. So what is the sole purpose of feature map, feature extraction? So when you have a image and a set of images which you are passing to a convolutional neural network, so how exactly is it able to capture the patterns present in the images? That exactly is done by this translation invariant property or the transposition property of your CNN, which is able to extract the features. So feature engineering or feature extraction of the important features of an image is going to be done by the CNN and going to be passed. So you're basically passing it to build a feature map. So feature map basically consisting of the important features or the most relevant features out of all the features present in your image. There may be some irrelevant features like noise, which can be added in a low resolution image and so on. But your CNN is very intelligent enough to identify which features are exactly relevant for it to train upon, and then it's going to pass it in a forward pass or in a forward feed forward neural network is going to pass it to the front layers. So when I say about the images can be your color, the color of the image, or the texture, and then also some other features like the edges present in the image and so on. All such are going to be considered as your features of your image, and then a feature map will be built and finally will be passed to the further layers like max pool layer, then the max pool layer basically to reduce the dimensionality of your image, and then your the final layer, which is a fully connected layer. Then finally it's going to be passing it to a activation function to basically overcome the non-linearity in your data set. As we know that the image data set is definitely non-linear, and there is going to be non-linearity introduced somewhere in your data set. So when you have non-linearity introduced somewhere in your data set, that is where activation functions will be very handy. So when I say activation functions, when you talk in context of binary classification, say mask, when I introduce you the topic of the face mask detection. So there are two categories basically, or two classes. A person having a mask and person without a mask. So when I say these are the two classes, it's a kind of a binary classification. So for those kinds of scenarios, you're making use of the sigmoid activation function. There's another activation function like softmax activation function you can make use of, and that comes when you have multi classes or multiple classes to detect. So then you have the final, what I mean was in the final, you have the activation function and finally the output. Now, what is the output of this object detection? The output of the input definitely is a set of images or a set of videos having different image frames. The output will be basically a labeled image or an image consisting of objects with bounding boxes drawn. Now, what is this bounding box drawn for? Bounding box is basically done on a technique which I'll be delving into, that is called as region proposal. So when you talk about YOLO, or say when you have the fast RCNN and other such object detection models, they are going to identify your target object by making use of selective search algorithms. They can make other algorithms also, like you can make use of your different like ROI pooling, region of interest. So basically, what is this clustering of pixels going to be done upon? So basically similarity measure is going to be done. So say you have two objects which are very different to each other. Easily the object detection model which you built will be able to classify and distinguish between the two objects which are really very different. Say a monkey and a cat, they look very different. So based by extracting the features of the monkey. Now, when I say talk in terms of the animals, the features of the monkey can be its nose, eyes, and so on, the facial features. And similarly, that of a cat will be its nose, eyes, hair, whatever, the facial features. So taking those features into consideration as the criteria for classifying the different objects, your CNN is going to classify them into different objects and then going to label them as a cat or as a monkey. That exactly will be done in image classification as well. But how exactly do you think this image classification is different than an object detection? Along with the classified category, you will also be getting the bounding box. Basically, the bounding box will be drawn in your image to detect the object, and along with that a score will be assigned. So that will be your output basically, which will be nothing but an object with the image containing the objects which are detected, and that detection is going to be done by a rectangular box which I showed you. That is nothing but the bounding box, and that is that is based solely on your region of interest or the target object detected, based on the region of interest or the region basically the proposal region network. So now you can also, I'll be covering this part, training your own object detection model later stages. So that is where you can make use of custom object detection. So first, if you understand what is object detection, how different it's from image classification, and which kind of data is actually needed for the different object detection models, then we can also get started with the custom object detection, where you can use your own, instead of using already a pre-trained model or some other data set, you can also use your own object detection model for making use of, and that technique is called custom object detection, which I'll be covering later. So when I talked about this, then another you can get started with is the face detection model, and that you can use OpenCV libraries as well over there. Like you have the Har Cascade classifier. If you learn the Har Cascade facial frontal classifier, so that is where you can make use for detecting the different features of an face, and how exactly you can basically identify the face of people present in an image. That can be done by building a face detection model. So then vehicle counting model, to basically, now when I say object detection, another area or use case of object detection can be counting the objects present in an image. So it is not only for detecting the object, but if you want to count the number of objects, say the vehicles in a road, that is an image when I showed you before, how exactly is our model being able to count the number of objects or count the number of vehicles present in the image? That is where vehicle counting model, or counting where you have a photograph of people, how exactly you can calculate the number of people present in the photograph. So that is again counting model come into picture. Then few furniture recognition models, similar to furniture recognition model, I can say there is, like, if you want to basically in your supermarkets or in a shopping mall, if you observe, if you want to find out basically what are the anomalous products available, so you can make use of such recognition techniques or build object detection models as such, which will be able to detect if there is any fault present in your item. So detecting and capturing the fault present in an item is a very prominent example, which can help the different manufacturing industries as well to detect the faulty items present in their manufacture. So whenever you are basically talking about the the supermarkets as well, before they get their before they get their materials or their products, so you have to basically identify the defects or the anomalies present in the product. So in order to do that, you can make use of such object detection models, which will be able to recognize and give you where exactly the anomaly is present. That is one another example. So these are some of the other advanced object detection models you can also look into. That is nothing but vehicle detection in video data. So if you have a video data of moving objects, so there is a concept called frame differencing here. So when I told that a video is a combination of different image frames, so you know that frame differencing is where an assumption that no other object in the image except for the vehicles are moving. So if you assume that only enough basically in a video data of different consisting of different moving vehicles, all the vehicles are only moving, and the other objects such as the pillar or say the road, these are all the static objects. So how exactly this frame differencing works is that the pixel difference, as you know, the image is containing of a combination of pixels. So the pixel difference from the first and the second frames of the video will highlight the pixels of the moving object. So when you see a kind of a difference, so frames are basically when you stop the video in different seconds or different intervals you set. So the first frame is having a pixel value. The second frame might have a different pixel value. So the difference between the pixel values of both the frames will indicate there is a difference in the frame. And that frame differencing in the pixel values will help you detect the moving vehicle in your image. That is an example where you can understand the concept of motion detection present in any kind of videos, which are dynamic images and so on. So once this is done, there is another example where object detection can be used, and that is surveillance camera, as I was talking about. whenever you want to monitor and track in real time basically detect objects in real time CCTV data. That is where surveillance camera object detection system can also be used. Then you can also go through this and deploy the object detection model on websites, web, and so on, for motion detection system, which I already talked about, and so on. So now that you've got understood that there are variety of applications where you can make use of object detection, let us now quickly understand what is the difference, which is between the small difference between image classification and object detection. So image classification, as you see on my screen here, is just going to, you're passing an image of a leopard here to a neural network CNN, and it's going to give you the class basically, that whether a yes or a no value basically. So this is a case of a binary classification because there are two classes, yes or a no. So it's going to just give us whether the input image is a leopard or not, and if it is a leopard, with what confidence score it is a leopard. So the score I was talking about is called as the objectness score or the confidence score. That is a particular threshold you can set. So if I say here 0.9495 is the confidence score. So it is, the model is 95% confident that the image is of a leopard, or the object detected in this particular image is that of a leopard. So this is where image classification will be very handy. So it is a computer vision task again, similar to object detection. You have the image classification, as I've told. That is also a computer vision task of identifying the content of an image and then segregating the objects into classes. So you're segregating the objects or detecting the objects into different classes. But then when you talk about object detection, along with the segregation of objects or the objects being detected, you are also getting a localization or the position of your object present in the image. That was the main difference between image classification and object detection. Now, what exactly are these kinds of image classification? And you have to understand that, see, image classification and object detection, they fall into the category of supervised machine learning. Okay, so as you know, machine learning can be supervised in nature or unsupervised in nature. But image classification task and also object detection task, they come into the category of supervised machine learning. So basically, supervised is where you have labeled data. So you have to note down this important point, that whenever you are performing object detection, you should always take images and annotate them. So data annotation or image annotation is very important concept, because along, not only the images should be present, but along with the images you should also assign some labels to the image. So because of that, it's called as a supervised ML. So how exactly is the data annotation or the labeling done? You can make use of tools like open source tools for image labeling, and the most popular one is Label IMG. Label IMG is a tool, and you can make use of definitely other tools also. So basically, you can manually label the images present, or label the objects present in the image accordingly, and then pass it to your training, to your model for training. Now, once the model will understand what are the labels assigned to it and gets trained accurately with so and so number of epochs you assign, or the different hyperparameters you tune, then it's going to basically accurately give you a prediction as to what object is present in the image and with what confidence score it is present. Now, this model is going to be trained upon some confidence score or objectness score you can set. In general, you have something like 0.95, which I say. Let's take the example. Okay, let's take example of 0.5. That is the objectness score. So if I say, if the objectness score, the confidence with which the model is giving me this class is, this object is present in this class is 0.5, is less than 0.5, then we say that the object is not present in the image. But if it is, the objectness score is more than 0.5, then we can say that an object has been detected in the image. So that is kind of a threshold you can tune again. This comes under the category of the concept of hyperparameter tuning you can go through. So you have basically in context of deep learning, definitely convolutional neural networks are used. And when I talk about the different the object detection models as well, like not only YOLO, but you have single shot detection like SSD models, and then you have different object detection models like fast RCNN and RCNN models, or faster RCNN models. These are two pass basically. Instead of being single pass, they are two pass or two stage approaches for object detection. So those are RCNN, fast RCNN, and faster RCNN models. So we'll be looking into that. So those are coming into the category of deep learning models. But when I say the algorithms for machine learning, some of them for classification can be support vector machine, decision trees, and k nearest neighbors, or KNN model. So once that is done, basically your CNN is able to classify your image into different categories by extracting the features, as I told, feature extraction, and to get the highly accurate results. Now what next? So basically this is the gist over here, which explains how CNN is performing the image classification. As I've explained, you have the different layers that you have the convolutional 2D convolutional layer, followed by the extraction of the features, and then that the feature maps will be extracted, then non-linear activation function. Then you have different layers apart from the 2D convolutional layer, which is 2D convolutional layer is basically for performing the convolutional operation. Now, you know, convolution is done by the concept of padding, strides, and you have to understand the concept of filters there and kernels of an image. But what exactly is max pooling layer now? Now, max pooling layer comes after your 2D convolution layer. Definitely, you can build your network by adding more and more layers so that your the more the number of layers, the more training the model will be better trained. So max pooling is where it's going to extract the most important features and reduce the dimensions of the image. So as I've told, to reduce the dimensionality of your image data or your training data, max pooling layer is set accordingly. Then you can replicate the model to go deeper into your layers. Once that is done, you can see pictorially over here to understand better. These are the different convolutional layers, convolutional 2D layer, and then you have a ReLU activation function. Activation function, the purpose of an activation function is to add some kind of a non-linearity to your data. So whenever you see that there is non-linear data, you can add over here rectified linear unit. So ReLU stands for rectified linear unit activation function. Definitely you can make use of different activation functions, optimizers. Generally, as I've told, the most important and the most better efficient kind of an optimizer is a Adam optimizer. But that the purpose of different optimizers and say gradient descent or learning rate epochs, that can be set accordingly. So more the number of iterations you train your model on, the batches you train on, the better it is. So that can be fine tuned. It is sent to your max pool layer to reduce the dimensionality of data, followed by again the conv 2D, then the max pool layer. Finally, you have something called as a fully connected layer. Now, what is this fully connected layer? It is a non-dense layer basically, and that is wherein every node of each layer is connected with every other node of the other layer. And the purpose of your fully connected layer or your FC layer at the end is for classification. The first the first layers over here perform the convolutional operations, basically identifying and capturing the patterns. But then the final one, after your features have been extracted and the patterns have been captured by your CNN, the fully connected layer at the end is going to perform the task of image classification. That is going to be sent, and finally the fully connected layer will consist of a sigmoid or a softmax activation function, and then give some probability to the prediction. Now you have to understand that what is exactly probability and why is it important. So once I have told the confidence score I was talking about, 0.95, that is nothing but a metric, and that metric is an objectiveness score or a confidence score, which is nothing but the probability of prediction. So how probable is that the object that is output over here, as you can see, it's that of a cat, yes or no? But then it is assigning some kind of a probability score to it. Now, the probability of prediction can be 0.95, 0.5, 0.3, and so on. So, with what confidence is the model giving us the answer is nothing but the probability score, the probability of the prediction. Now, image classification, one core application of image classification is where the object detection comes into picture. So nothing but both of them are almost the same, but the core thing you have to understand is that object detection is not only, as you can see here, giving us a bounding box surrounding the object detected in the image, it's also going to give us the value or with what confidence it's doing. Not only is going to give us a class of the image, but is on the whole image, but rather it's going to give us a bounding box along with that is the region of interest, which I was talking about, the area of interest or the region of interest. Then associated it for the input, and along with that, along with the class label, you'll also be getting some score. As you can see, cat 0.90 and dog 0.85. Some kind of an objectness score will be assigned along with the label to your object detection output of your object detection. Now, what exactly are the object detection methods? So there are two categories, that there are one-stage methods and two-stage methods. So one-stage methods, you have to understand that they have only a single forward pass basically. And the most important one stage methods, and they are more preferable as well. You have to understand that one stage methods are more preferable as compared to two stage methods, because two stage methods are extremely slow. As the name indicates, you have to, there are two stages involved, so they are slow in nature. But one stage methods, they are comparatively faster, accurate. In some contexts they are accurate, but then definitely they do have drawbacks as compared to the one stage methods, two stage methods we'll be looking into. But one stage methods, like you only look once, YOLO model is one stage method. So as you can see on my screen here, the input image is divided into grid cells. As you can see here, this is an input image having S cross S grid on input. It's going to be divided into some, different grid cells, and those are going to be fed to the model for categorizing or assigning the bounding boxes. So the computation of the bounding boxes is going to be done based on the similarity of the pixels. So when I say similarity of the pixels, the similar pixels are going to be grouped or clustered together by the model, YOLO model, and then along with that, the grid cells, basically along with those bounding boxes, you'll also be getting a class probability map or some kind of a score, class probability score going to be assigned. So when you see that the center of the bounding box falls within the grid cell, then the coordinates and the class confidence scores are calculated. So the class, if you see in the final detection, there's a dog which is identified, then a bicycle and a car which is identified over here. But with what measure, with what confidence it is identified is also going to be retrieved and given in the output of your YOLO, in the YOLO model. So that is where you can make use of one stage methods like YOLO, and there are different variants like YOLO V1, V2, V3, V4, and V5, V6, until V8. Of course. So when I say what is the best one out of this, there is nothing like best, but then definitely the more later ones are faster in nature and more suitable if you have large data sets. So what do you think can be the disadvantage now that it's very advanced? YOLO is very advanced one and most prominent one in fact, but where do you think it can actually have a drawback? So YOLO basically, what happens is when you have that wherever you have very small or tiny objects to detect, over here the objects to be detected are nothing but large enough. You have the bicycle, car and a dog. They're large enough, but what if I say they are very minute and fine details that has to be captured in the abstract representation of your image? So that has to be done whenever you want to identify the objects present in image which are very small in size. So in that cases, YOLO will not perform better because it's trained on large data sets. So it works on large data sets, but when you have less data or small data sets, then I say that you can go and explore the other object detection models. And definitely one thing you have to understand, the concept is that basically YOLO V5 is fastest, but then YOLO V3 fastest is compared to faster RCNN. So when I say fast RCNN, that is a two-stage algorithm or a two-stage approach. So in comparison to fast RCNN, YOLO V3 is better, but then YOLO V5 beats that as well. And because YOLO V5 is the most recent one, so definitely it's more preferable to use YOLO V5 even for large data sets. So when I say SSD stands for single shot detection. The basic working of SSD is very similar to that of a YOLO, but the core difference between SSD and YOLO is that whenever you have objects to detect objects of varying scales, that is where single shot detection, which is SSD, comes into the picture, and that is again a single stage approach. So although SSD is quicker than YOLO and gives more accurate results, the performance slightly reduces when tiny objects are. So when you have very tiny objects to detect, then in comparison to SSD or single shot detection, YOLO works better. But then comparison to YOLO and SSD, we can say faster RCNN and fast RCNN, which is two-stage methods, will be preferable. So you can see, depending on what kind of data you have, whether you want to detect or what kind of use case you want to detect. You want to detect the number of, basically the large objects, or you want to detect very minute details, like say, for example, detecting or identifying the faults in different products. When I was talking about that, the anomaly detection of different products, that is where very minute details have to be noted down, like cracks and crevices. So in those cases, we can say that two-stage methods will perform better. Now, coming into before getting into two-stage methods, there's one important piece of content for YOLO algorithm which I want to explain it to you. You can see in this image, the final detection will be something like this for YOLO. But you have to understand that in comparison to the two-stage methods, which make use of both RCNN, that is nothing but recurrent neural network RNN, and as well as convolutional neural network or CNN. So along with instead of that, instead of performing the region of interest and ROI pooling on the max pooling layers, YOLO only uses a single CNN. So a single convolutional network is only used there to perform real-time object detection. And the CNN model predicts the class probabilities for the detected objects and applies bounding boxes for the detected objects in an input image. So along with the bounding boxes, you're going to get the class probabilities, as I've told. But it requires a single forward propagation through the model of object detection and prediction in an input image. So that was all about YOLO in the first place, and you can compare it it's very similar to FCRN or fully connected neural network, very similar to that kind, because that if you're passing in an n cross n image, say you passing in a size n cross n, dimension of the image is n cross n as input to your FCRN, but the output will be an m cross m image. So prediction will be an M cross M image consisting of bounding boxes and class probabilities for each bounding box. So that is where, similar output, the output images will be similar in size, although the images which are passed as input to your input image may be of differing, say, the data set of images having different sizes. But then the output, what you will be getting is a data set or an output of images consisting of images of same sizes. So that is one aspect we can say that why YOLO is very preferable and is an advantage. So that was all about it. Computer vision applications of YOLO are endless. Like, you can make use of different YOLO architectures as well. You have to understand that you can process videos and images and videos at the rate of 45 frames per second, and 45 FPS, that is frames per second, to 150 FPS, giving better results than real time. So that was all about it, and you have to understand that the training time for CNNs like the RetinaNet is greater than for YOLO. So RetinaNet is again a CNN. If you compare RetinaNet with YOLO, although RetinaNet is taking a lot more training time, but then YOLO is much accurate than RetinaNet. So that is where YOLO is very preferable. But as I've already told the disadvantages to you, when you have smaller data, it has low recall, firstly, low localization error, but then it does not detect objects which are close to each other accurately, since each grid in the image can only have two bounding boxes. So basically, to detect objects or identify objects, you need bounding boxes. So but then the maximum limit that the YOLO has is only two bounding boxes. So for detecting objects which are very close, there is not much proximity. The images are very the objects present in the image are very tiny and also approximately present in the image. In those cases, we do not go with YOLO and we can go with some other algorithm. So it fails to detect small objects in an image. So that was all about YOLO algorithm. Now coming to the two-stage methods, I would like to explain. I would like to first explain you diagrammatically like this. If you see what exactly is two-stage method, they have two stages. Now what is the two stages present in a two-stage method? You have to understand that unlike the one-stage method like YOLO and SSD, the two-stage methods which are RCNN, Fast RCNN and Faster RCNN, the two stages which are present are firstly the region of interest pooling is going to be done. So if you see in my screen over here, the input image is going to be passed to a convolutional neural network, convolution network, then regions of interest or ROIs from a proposal method. So you have a RPN basically, or region proposal network, which is followed, or ROI pooling. So a region of interest is going to be computed based on the selective search mechanism. Now, what exactly is selective search? Selective search is prominent in your RCNN. It's RCNN, not in the fast RCNN, but in your RCNN, you are going to be making use of the selective search mechanism, where basically this, pixels which are very similar in nature are going to be clustered. Although it's very good, but then the purpose, why RCNN does not perform better and why it's very slow is because of its, it's very time consuming in nature, firstly, and you have the problem of multiple and overlapping bounding boxes. Now this is a very important and an intricate concept that you have to keep in mind wherever you are performing object detection. Now when I was talking about object detection, you have to detect objects by marking the marking the bounding boxes, and the coordinates of the objects will be given in the output. But what if your image or the output image, you're getting multiple bounding boxes and they are overlapping? Say there are different cat, dog, and very different objects present in your image, but then the bounding boxes are overlapping. They're like coming, they are superimposing each other, or they're coming next very close to each other, and they are multiple bounding boxes. Say you have only 3 or 4 bounding boxes, it's fine. It's easier for us to identify which are the objects present. But then if you have multiple bounding boxes, those are the problems which commonly occur in object detection. So in order to reduce or overcome those cases where you have the problem of multiple bounding boxes or overlapping bounding boxes, two techniques is something which I can propose to you. The one thing is where you can use custom object detection, wherein you can just use pre-trained model, apply transfer learning concept there, and by making use of pre-trained model, you can just retrain the model by training it on the fully connected layers or the last layers of your neural network. That is one way, by making use of a customized data set of yours. But the other way is by, instead of whenever you see that the bounding box is coming, there is an algorithm called NMS, that is non-maximum suppression. So non-maximum suppression is one such object detection concept which is prominently applied where you have the problem of multiple bounding boxes occurring. So in those scenarios where, like in RCNN, multiple bounding boxes is very commonly to be occurred. So NMS is commonly applied there, and non-maximum suppression, which is going to ensure that the number of bounding boxes or the overlapping bounding boxes will be reduced and the problem can be overcome in nature. That is one case. And also, more the number of convolution operations, definitely the size of the image will also reduce. So in order to preserve the size or the suppression of the image, you can make use of the NMS algorithm. So basically, as I've told here, everything works in the two-stage method. The second step is classification. The first step will be region identification or the region proposal, which is your region of interest is going to be identified. Then the second step will be your classification after your feature extraction. That is one other thing. So in RCNN, it's going to use a selective search method, as I've told, but then the drawback is that selective search is, is very manual and it's also going to take a lot of time. So in order to overcome the drawback of RCNN, Fast RCNN was the CNN model which came up. And in this method, instead of passing region proposals, so instead of passing, region proposals or the basically a part of an image, the clustered part of an image which you did using the selective search, instead of doing that, the entire image is going to be passed in as input to your Fast RCNN. Once the entire input image is going to be passed, the whole image is passed to the Fast RCNN. It's going to calculate the feature maps after feature extraction. After calculating the feature maps, later the region proposals are generated from a proposal method, and the ROI pooling, which is very important here, the region of interest pooling layer is used, which reshapes all the regions for input to the model. So finally, a fully connected layer will give you the bounding box along with your classification values. So the object is going to be detected in such a way. So you're going to get, after the fully connected layer, the output. This is the case of Fast RCNN, and as you know, Fast RCNN beats the RCNN in terms of the training time as well. So it is much faster as compared to RCNN, and also Fast RCNN over here, Fast RCNN is also faster than YOLO V2. So YOLO V2 and V3, they lack in speed when compared to Fast RCNN. But then YOLO V5, starting from YOLO V4, V5 and so on to YOLO V8, they are faster than Fast RCNN. So that was all in terms of the time which I was talking about, that is the training time and also the accuracy. So once that is done, and also Fast RCNN, RCNN as well. RCNN, although it's very slow, it is really accurate. Why is it accurate? Is because of the selective search mechanism. That is, the area of interest is going to be first identified, and then ROI pooling is then going to be passed to the max pool layer, which will then pass it to the fully connected layer, as I've explained over here. As you can see on the screen, it's going to pass the region of interest and to the fully connected layer, and then finally the output will be your bounding box regressors. That is, along with classification, regression is also going to be applied. Now, how exactly, you might come across this question now when I was explaining, when I told you that a bounding box is going to be drawn, and then that is nothing but a regression technique. But why exactly is it regression, and how do you think that classification and regression both can be done by these models? Definitely, you have to understand that image classification is not only, this RCNN and the Fast RCNN models, YOLO models, they're not only limited to image classification, but along with image classification, you can also add optimizers to them and also perform classification and regression both. So RCNN stands for region based, basically, since you have to calculate the area or the region of interest. So that is why it's called as region based CNN or region CNN. So that is called as that is why it is shortened to the form of RCNN. So basically, regression can also be performed on classification along with classification by these models, is because the data or basically the trained images or the trained weights you have used for performing the classification task, the same trained weights you can use it for performing the regression task. Something like your transfer learning concept only, you can say, because you're going to transfer the trained weights or the pre-trained weights basically on once your model, CNN model, has done the classification task, you can use those weights and perform the regression technique as well. That is why it can perform classification along with regression both together. So coming to the faster RCNN, it is more efficient than RCNN. It, although it, the difference is that it uses selective search also. Like if you see RCNN, it is also using selective search, but it is faster and more efficient than RCNN. And faster RCNN is fastest among all the two-stage methods. So it makes use of region proposal network. Now you might have thinking that fast RCNN was also using, but then fast RCNN was using region proposal method. The region proposal was passed in as a function or a method to the ROI pooling followed by the feature maps. But then in faster RCNN, we have a network. Instead of just a method, we have a region proposal RPN network, which is used to predict the object regions and objectness scores. So objectness scores is nothing but, as I've told, the final confidence scores we can see, or the probability scores assigned to the bounding boxes of the objects labels. So RPN is CNN that effectively learns the proposals along with the ROI pooling and fully connected layers remain the same. Fast RCNN, the faster RCNN learned region proposals and works faster than RCNN and fast RCNN. So it is faster when compared to the other two models, the former two models, but then it also creates learned region proposals. Now, what is this learned region proposals? It's because of this RPN network or the region proposal network which is present in the faster RCNN. So now that you have understood, definitely you can now understand what were the different object detection models and how exactly the object detection is applied everywhere in real life. Like when I say semantic segmentation is nothing but when we, instead of classifying the whole, basically classifying the entire image into different categories, you can make use of semantic segmentation to classify or assign classes to different pixels of an image. So as you can see, the image is containing various pixels. So instead of doing object detection on the whole image, on different on the granular level, or basically on the finer details, when you want to calculate basically extract the abstract representations present in image, that is where semantic segmentation will become very useful, because it's going to classify the every pixel of an image to a corresponding label. Basically assigning or labeling every pixel of an image is where semantic segmentation can be used, and definitely it can come very handy if you use fully connect convolutional network, FCN. UNet is another faster one. You can also look into this UNet architecture, how the maths behind it, delve into the core aspects, why is it called U? Because it's in the form of a U. And not only that, but because it's making use of the encoder decoder to retrieve the intermediate feature maps. So this is where the intermediate feature maps in the bottom layer is used here, along with the encoder and the decoder. And then you have different skip connections which are together forming a U-like structure. So that is why it's called as a UNet architecture. Then you have the deep lab and other advanced models as well for object detection. So this concludes your topic about object detection, and later we'll also be looking into how exactly custom object detection models can be formed, and I'll be demonstrating a Python code as well to show you how you can use YOLO V4 model for building a custom object detection model in Python. So thank you very much. And as you know that Project Pro is basically a curated library of solved end-to-end project solutions, that all the projects you can find is created by top industry experts working in the top global tech companies. So you will find here various code recipes, tutorials, blogs, and whatever you need. So 24/7 customer support along with the guided videos will be present here. And not only that, you can find tutorials as well, different projects which are touching real life business use cases. So stay tuned to the Project Pro YouTube channel, subscribe, like, share. Thank you.
Project Pro, the only solution for solved industrial grade projects.